Right. So Devadita is going to talk to us about efficient forward architecture search. So this is a very fast approach to doing neural architecture search. Go ahead.
Thanks, John. So today I'll talk about a method for doing neural architecture search. But before I even talk about a particular method, let's see, why we care about searching for architectures, right? So this was when I was visiting John in New York in April 2018, and this is actually a picture from dense nets, right? And actually, wait, before we even begin, how many of you would say are very comfortable with at least basics of training a neural network, right? Okay, great. And TensorFlow, PyTorch, or CNTK, one of those. Supervised learning, you have trained a neural network on some data set. So often what happens is that, hey, we have to figure out how many layers we need. And let's say this is a data set that is new, right? It's not a standard, well-known data set on which there has been a lot of communal domain knowledge, right? Like people have tried stuff, published stuff, but this is your own proprietary first-party data set, and it's massive. So what should be the capacity of your network? What should be the particular stride length, or how should you connect these things to each other, like the layers to each other? And this is all very frustrating, right? And you are sitting there and you are trying things, and you have an org GPU budget, I am sure. It's not unlimited, and you want to try out many of these things, and you want to achieve some kind of performance that you care about, right? I want good performance. I don't want to use too much GPU RAM, because during production time, that means I have to allocate too many machines for serving. I also want it to not have more than this much latency. So there are all these multiple objectives that you want to ideally do. But even before you get to all of that, in the beginning, you have a new data set, new task. You just want to figure out something that works reasonably, right? And let's stick to supervised learning. We are not going to talk about reinforcement learning. We will talk reinforcement learning in the solutions methods, but we will not. The tasks will be supervised learning, right? And so. And here's the truth. Nobody really knows how to set these things, including people who are experts in the field and have invented neural networks back in the day, right? This is all trial and error. This is very empirical work. And this can feel very magic, we have all these magic numbers floating around. And not only this, we have magic numbers floating around in the training parameters, right? That is not even in this picture, right? What's the learning rate? What's the learning rate schedule? How should we warm start? What should we initialize the weights as? And this is the big motivation for trying to take this guesswork out of humans into the hands of algorithms, right? And hence there is this very nice subfield of machine learning now called neural architecture search. And we have all these problems we talked about, and there's also a massive talent shortage, right? And I think this room has a biased sampling, but in the real world, getting people who have the right skill sets and hiring them and training them if needed is not easy, right? And if you are out there in the field, you probably know this much better than I do. So we are going to do first, before we dive into our particular method, a 15-minute literature overview, right? And before we even go there into the literature overview, we are going to look at okay, what is the problem definition, right? So the problem definition is we have a search space. And remember, this is not very difficult, right? This is not very complicated. All I actually want to do is, given a search space, which is the set of all realizable, neural network architectures, I want to find an architecture that fits my, all my criteria. It has this much accuracy, this much latency, this much things, if possible, or come as close to them as possible. And I'm done, right? And a training procedure that hopefully can train it, and I'm all good. As with any search algorithm, this is no different than any search algorithm, right? If you're doing search in any ways, all the same things come into play. There's some challenges, which is the third column. But the first one is we need a search space, right? If you're searching something, you need to define a space to search in. And we will see that there are usually two kinds of space. And in the informal lingo, they will either be called macro or micro. And we will see examples of that. And a lot of right now, domain engineering goes into what should be the right search space. Because here's the trick, right? Like if I can somehow come up with a search space which I know will have all the right primitives, like it has the conv layers, it has transformers, it has self-attention units, and all of these things, batch normalization, and all the right operations. And I can also inject some priors into the search space that, hey, I know that if I have a conv unit, after that I should not be doing a batch normalization this way. I know that layer normalization works from other empirical papers. I can prune out the search space by just injecting a lot of human domain knowledge, right? And that itself, and there's debate right now is how much domain knowledge should I inject into the search space, and which ones should we work on, right? So we will look into some details of that and pros and cons. Now, once you have a search space, the big problem in architecture search is that your search is very expensive, right? So because here's what really happens, right? In order for you to try out architectures one after the other, what you like and find the right one, you literally have to somehow find an architecture, train it all the way to the end, and imagine you have a data set which is ImageNet size, or if your language, this is like training a BERT model or something, right? This becomes your subroutine. There is some algorithm, which is search algorithm, which is searching for architectures and giving you an architecture somehow, and your worker threads have to go and try them on your data set. And then they will report back some statistics like, oh, this particular architecture has this much memory usage, this much latency, this much accuracy, and so on. And you will take these data sets and update your search algorithm on what to try next, or what other things to try next. And all of these things actually happen asynchronously in any proper implementation. But all the expensiveness of neural architecture search comes down to the fact that every time, in order to evaluate a point, function evaluation is super expensive. So I have this search space of neural architectures. I pick a particular point. That point is an architecture. I have to go and train it. And this training can take on 4 GPU box, 2 days, right? So this is super expensive. So and there are uncountably many of them, right? Depending upon how I define my search space, there could be easily these are discrete things usually. I'm putting aside continuous hyperparameters, so they are not really uncountably many. But easily you could have millions and millions of things to try, right? So which ones should I try? I don't want to use 10 million hours of GPU hours, right? And okay, so the search strategy is all about how efficiently can we search through the things. And then performance estimation is more like a subpart of search strategy. Is when I'm searching, when somehow I'm like, oh, looks like a good candidate to try by using whatever algorithm, I'm going to go down and see how well it performs, but I don't want to actually train it for 2 days. So let's say it takes 2 days to train an ImageNet size data set on an 4 or 8 GPU box. How quickly, how approximately can I evaluate that function, derive a reliable signal of how well it performs or not, and get out, right? Without being fully committed to it, right? Because that takes up a lot of time. So usually, if you look at neural architecture search literature, most of the differences are along these 3 dimensions, right? What's your search space? What's the strategy? And how you are doing performance estimation to do things. Okay, so let's look at define some of the search space terms, because this is important, right? So this is what is called as a cell search space. And what happens in a cell search space is, let's see, how many of you are familiar with, let's say, ResNet? Okay, good. So if you know ResNet, you know that what happens in ResNet is there is this really nice skip connection, and there's a ResNet cell, right? And there are regular cell, and then there's a reduction cell. That's to downsample the resolution, increase the number of channels, so on. But really in ResNet, the design is not that complicated. If I want to create there is a cell which is basically this little motif structure right here. And in ResNet, all the cells are the same. In this one, it's a little bit more general. The motifs are different, and all the cells, and you have all you are doing is lining up the cells and connecting them via skip connections, right? And if you want, let's say, oh, I want a bigger thing, hey, add more cells, right? And all the cells are designed the same. And this is very popular in literature because the nice part is you can inject a lot of human domain knowledge, right? And reduce the search space. Your search space is not fully general. So let's say you say that like, hey, I'm going to use the ResNet-like backbone, which is the skip connections that you have between cells, and I'm going to keep the search space constrained to finding what the motif should be, the cell should be, right? And then if I want a bigger network, I just add many of these cells together, stack them, like just stamp many of these cells together, and I get bigger networks, right? And as you can imagine, instead of you are not searching for what the outer skeleton should be, and this really reduces the number of things you have to try, right, with the number of your search space. There is a lot of human domain knowledge injection. So some smart people came up with ResNet, and we are going to utilize this information that skip connections are good, and having these cells is enough, and it seems, and we are going to figure out what the cell design should be, right? And this is the most popular search space. And then, of course, there's the other one, which is what you would actually expect if you didn't know about the cell search space, right? Which is like, well, I have like a fully general search space. Anything goes. Any particular type of connections, and any size, any wonky, weird shape is all on the table, right? And this is obviously much, much bigger, right? And a lot of research shies away from using this kind of search space because, hey, even for doing this research, you need a lot of GPUs, right? And I will show you results later that will show that actually you can use this kind of search space and you can be competitive with cell search space even if you use a much bigger search space and get similar results, right? And okay, so this right now, the slides we'll make available either through the website or email me. So all the links will be there, so you don't need to worry. Some really good people maintain this really nice list of architecture search papers, right? And to just give you an example of how hot this field is, let me see. Okay, so actually, wait, the browser is on. So remember, we are only in October. There's 2 months left in the year, right? So this is so there's a group in Freiburg who maintains this list of machine learning papers with in neural architecture search related papers, which either are published or not published, and I think the bold ones are published. And this is 2019, okay? And I'm scrolling down. We are still in 2019, okay, a little bit more. Oh, we are still in 2019. Even I'm surprised. I didn't expect I had to do so many. Okay, 2018. I see 18, good. 18. Oh boy, even 18 was pretty big. Hey, 17, this is good, right? 17 will be much shorter. 16. Whoops, and then the list ends, right? And from 2017, 16, you go all the way back to 94, 90, 89, 88, okay? So there was this big gap for I forget how, do the math, 25 years or something, where we didn't do anything on that topic, right? And so this is pretty incredible, right? I think there are 50 to 60 papers on arXiv every, I dread waking up in the morning and looking at arXiv, okay. So, and there's this really nice survey article I recommend reading because as happens with any field in which is going viral, do you need to read all the papers that came out just this month? You will have to give up your day job and just sit and read that, right? You don't have to. That's the good news because a lot of it is noise and there are few key ideas that you really need to know if you want to know. And I recommend that survey paper for more details. And within this short thing, I'll spend 5 more minutes to talk about 3 or 4 key papers, right? And then we'll move on to our paper, which will come out in December, but it's on arXiv. So the thing that actually started, or I should say restarted the the modern era of interest, right? Like in architecture such. And as you saw, like, this is not the first paper, right? So this is probably like the 10th or 11th paper. The first paper was 1988. The second paper was 1989 at CMU. But this one really, like, restarted. So 4 or 5 years into the deep learning revolution, reawakening, this paper came out, right? And this paper was super simple. Some of you, I think, took the classes on explore, exploit, and basics of reinforcement learning. So if you did, this should look pretty trivial, right? So I'm going to do this policy gradient method. And if you don't know RL or policy gradient, these words are alien to you. You don't need to worry about it at all. Here's the simple thing. I'm going to take one neural network. In this case, it's an RNN, which basically to get a sec-to-sec model, because we are going to encode neural networks as a sequence of outputs, right? Like, oh, it's conf5, followed by a ReLU, followed by a max pool, and so on and so forth. So this RNN is going to, like, output me by, like, unrolling the RNN. It's going to output me a network definition, right? And so that's I'm going to call that the controller. And when I get a network definition from it, I'm going to send it off to, let's say, a worker thread or a machine somewhere in the cloud, and I'm going to train it, right? On the data set. And let's say I have ImageNet or CFAR or something as the data set. Just to give an example, it will train. I will get some accuracy and some other statistics back. And I'm going to update this. So if I get if really good things happened for that particular, like, network that was sampled by this controller, during the update process, I'm going to update in such a way such that those kinds of networks will be more likely, right? There's a little bit of, like, very trivial math that goes into how you will do the update from this, but it's very simple, right? Like, you are just going to make the network, this network which spits out other networks definitions, make good networks, like the results of those training, more likely, and the other ones less likely. And we are going to use essentially like supervised learning updates, right, to do this. And to give you a very concrete example, that controller network goes along, unrolls, and it gives you this, like, number of filters, filter height, filter width, stride height. So this is one, this is layer n. And then you keep unrolling, and it will give you another layer, so on and so forth, until it issues stop, and that's your network definition. And this became quite popular, right? This is a very well cited paper. And unfortunately, and I will show you results comparing all of this later, this was extremely expensive. Like, to do even search on CFAR 10, I forget the exact number, but it was like 1,800 or 3,000 GPU hours, right? And this is probably way more than you want to afford, right? Like, in terms of GPU cost. So the next paper that came out made this cost go from like 1,800 GPU hours to obtain, like, a network which does well on CFAR 10 and ImageNet to, like, 1 day, right? So at that time, it achieved I think it beat humans at that time. Don't quote me on that though. On CFAR 10 and as well as on, like, Petri Bank, all those numbers have gone way, like, more accurate. Because this was 2018 and this is 19. So this is ancient by deep learning time, right? In all the experiments, they used a single 180 Ti GPU. Now this starts to look much more attractive, right? Like, because the paper before, even though it was the paper that started let's say restarted the interest, was pretty impractical, right? Like, that didn't seem like a good method. It wasn't efficient at all. This starts to look much more interesting and attractive. Okay, so let's talk about, like, how you go about doing this. They still did the same thing as before, where you had the RNN sampling, like, networks, and then you went and trained it, and you updated the RNN, and obviously you were doing all these sampling things in parallel. You sampled, let's say, 1,000 of networks in parallel, and you send them off to 1,000 worker threads and whatnot. But note the big expense. What is the biggest expense? The biggest expense is the cost of doing forward prop and back prop, right? Like, and mostly back prop, like, is much more dominating, and updating all the weights. That is, like, if I sample like 10 different architectures and I send them off, I'm doing, like, 10 times how many epochs times how many data set points are in every epoch, well, divided by the number of mini batch size, that many number of backprops. And that's where all my forward prop and backprops, and that's where all my compute is going. And this is the very expensive part. What if, so this was a completely crazy idea, and then this will look barbaric when I mention it, is what if it didn't do that? What if we, let's say, I sampled 5 architectures to keep it simple, and the 5 architectures are very similar to each other, except they differ in some edges, right? Like, I have one architecture, and it looks almost the same as the one next to it, except it has this edge, it doesn't have this edge, right? And let's share their weights, right? So I'm going to take those 2 architectures, put them in the same computational graph. So let's say they have all these edges common to them. I'm going to let them share it, and I'm going to do one forward prop and one back prop through these 2 architectures at the same time, and I'm going to update their individual loss functions individually, but the gradients are flowing back in aggregate, right? And so the edges which are not common, they only see gradients for each of their respective loss functions, but the rest of the network, they all see all the back gradients coming in. And this sounds crazy, right? But very efficient, because what you are doing is I'm just doing one forward prop and back prop, and let's say I have k networks, and all the k networks I can evaluate or train at the same time.
Are you saying that you're basically aggregating all these network structures together, so you have partially connected?
So okay, here's the example, right? So what you do is here's one big limitation. You have to assume that there is a big supergraph. There is this big graph from which which is your search space, which contains all possible networks, and you are sampling from that. And let's say, so this, for illustrative purposes, this is the big graph, right? The fully almost densely connected one. And this red one is one subgraph, which is a particular network, right? And that RNN sampled one of these, right? And I took it. And then I asked the RNN, sample me another one. And let's say it sampled another one which looked like, all these edges were common, but instead of this edge, it went this way, right? And maybe something else happened. So all these edges which were common, I'm going to create this new graph which has basically the superposition of these 2 graphs together, right? Take the union of those 2 graphs. So I will have some edges which are different, but all the other edges are common, and I will treat that as one graph. And I'm going to do just one forward prop and back prop through this superposed graph. It's not really superposition, but just take it as the union, right? So the edges which are there could be edge which is common across let's say 10 different graphs all at the same time. And this really amortizes the cost of search. So you come down from so you might ask why will this ever work? Because the edges should get specialized, right? So let's say there is an edge which is a part of k different graphs. Isn't this really bad? Because that edge is now trying to be good in terms of its particular weight values it will take on, trying to be useful to many graphs at once, right? Instead of specializing to the particular graph, each individual graph it belongs to. And the conjecture is that we have some good regularization effects, but this works, okay? And if you read the paper, I couldn't find any deep understanding of why this would or wouldn't work. In many ways, maybe you can think of it as multitask learning, right? You are regularizing the weights by saying that hey, you have to be good across many different graphs.
You're learning the same fast.
Multitask for the weights perspective, right? So the weights have to learn a value such that they are good across many different graphs. If you treat as every different graph as a task, right? You don't have to call it a task, but right, think I get some regularization effects. Okay, and you can use the same tricks to do get a RNN to sample another RNN, right? And in RNN, actually, what happens is your cell search and macro search are equivalent. There is no macro space. RNNs are cells, right? You are just rolling out the cell, so everything is nice, right? And so on and so forth. And if you look very quickly at the results, let's see. You come down from GPUs. Look at the number of GPUs. 800 GPUs. These are the number of days. that this was the paper I showed you. So multiply this by this. This is a huge GPU budget, and then we come down to 1, right? And after doing this, they were getting this, and now we come down to this, right? And there's also the params, number of parameters. So in almost every respect, you become this is a strictly better, uniformly better on all the fronts that you care about, right? So so this is a good paper to know. Okay, and look, and they discovered networks on image data sets that you will probably not come up with if you're a human being, meaning I don't know about you, but I will not come up with this, right? Like there's no way I will figure this kind of network out. If you're doing cell search, this was the kind of things, and this was the kind of things, but it doesn't really matter. But that the whole thing is that these are not intuitive things that you will sit and come up with, right? Very likely. Okay, this is actually my favorite paper, and this was with DeepMind and CMU called DARTS, which came out, right? And sometime mid last year. This one is nice. There is no reinforcement learning. There is no controllers. Oh, by the way, feel free to stop me and ask me questions anytime. It will be more fun that way. Because if you think about it, it was kind of weird that this thing, the 2017 paper, posed it as a full reinforcement learning problem, more so than that they posed it as a stateful RL problem and did policy gradients, right? And because you can actually have gradient information here, right? So this is like feature selection. So why would I pose it as the hardest possible setting? And then that's obvious in the numbers that you can come get back, that it's so inefficient, right, in finding something good. And there's some limitations here that they do only like cell-based, and you will see very quickly why they can't really handle big, large search spaces. And they did really well and in terms of search time. So here's the idea. And this is very similar to the ENAS idea, is that, hey, imagine the following, that I have got, so let's say I have, so this is a cell, right? And the cell, let's say, has 4 nodes, and this is just for illustration purposes, 0, 1, 2, 3. And the nodes here are tensors, and they're connected by operations, right? So from this node, so let's say going from 0 to 1, let's say I pick ReLU, then it will take the tensor at 0, apply ReLU to it, you get a new tensor, and I will make that, and that new tensor will show up at 1. And they said, you know what? We are going to, okay, usually this is a discrete optimization problem, right? If I keep the hyperparameters constant, finding architectures, it's a discrete optimization problem. I have to figure out, which discrete architecture I want. They did this nice continuous relaxation, which basically means that I'm going to consider soft weights, right? Weights over all possible architectures. So let's say there are 3, for illustration purposes, I have 3 operators, ReLU, conv 3, and max pool. And from 0, I can go to 1 or to any of these nodes by using any of these 3 operators, right? And depending upon which specific choice of operator I choose, I get a particular architecture, right, at every place. Right? I could instantiate a particular architecture based on, let's say this one was ReLU, this one was max pool, and this one here was conv, and so on and so forth. I get a particular architecture. But instead of that, I'm going to keep all possible architectures around at the same time. And I'm going to keep weights on them. So now we have 2 kinds of weights. We have weights on the architect, which are the weights that you would traditionally understand. Like if I have a conv layer, I have the weights and biases to train, if you have biases at all, to train in that. But then I'm going to have this new kind of weights called weights over the architecture. So I'm going to have let's say a weight alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, so on and so forth, where 1 alpha corresponds to 1 operation. Right? And if that alpha is very high, that means that the network, for example here, if alpha 2 is high, that means that the optimizer is trying to say that for this particular connection, let's say ReLU is really good, and for this one ReLU is really good, this one convs are good, and so on and so forth, right? But note that we are keeping everything around, but based on the optimization, whatever values of weights these take on are giving you like, a continuum of architectures, right? And then this is key. And then if I want to like, you will ask like, okay, but I want one architecture at the end of the day. You take the argmax over all the edges and you get a particular architecture, right? Take the best weight and the corresponding operations. So, and it turns out that you can do this. There's some optimization background, like there's this thing called bi-level optimization, where bi-level, the two levels here, as you can understand, is the inner loop is I want to train my network the regular way, and the upper level is like maintaining weights over architecture. So I'm going to do this inner loop and do this outer loop, and during all this time, okay, but this optimization is still efficient in terms of backprop forward prop, because my cost of backprop is amortized across all of them all at once. Because in order to evaluate these weights, it turns out that all I need to do is one forward prop and one backprop, and I can get to update this, right? So again, like INAS-like things of like now I'm going to just keep continuous values over all the architectures, and I'm happy. Right? So, okay, one problem that you might guess is, what do you think would be a problem with this? Like, that this sounds good. There's some problems. The optimization is approximate, and unless you delve into the math, you might not find. But practically, would you want to do this, right? Or what do you foresee as the problem? Runtime. So again, this is like less than a day, right? Like the results are really good, like at least on CFAR and ImageNet and whatnot, right? Yeah, they're just as good as INAS, but if not better. Something must really bother. Okay.
Yeah. So on those graphs, what does those 3 lines, right, on the trajectory? What does each line represent? I mean, have you done it like 3 times?
No. Each line represents a particular operation. It's an operator. So let's say you have a set of operators, like relu, max, pool, conf, and each line represents how much weightage you give over each one of those operators.
Well, the number of operators is like almost uncountable, because you can have any number of hyperparameter in terms of inside that operator, which makes it a new operator, right?
So assume the hyperparameters are constant.
Like if you're concatenating like 3 by 3, what if you do 6 by 6, or what if you do 12 by 12? See, those are.
So usually what you do is you have a bag of like 15 or 20 operators. Usually it's like 11. It's like conf 3 by 3 is one operator, conf 5 by 5 is one operator, and this is actually what you are getting at, is this other thing, like secret, which
you're greatly shortening, or
that's the search space.
You're constraining your search space.
You're constraining. Yes, and that's again like but that's not common to darts. That's common in any cell search space, right? Like so, you usually take this discrete bag of operators. Like conf 3,3 is one operator, which is distinct from conf 5,5, right? And they would just show up as different lines here. Your point is good. So if I have like many of these, then if I have 20 of those, I will have 20 lines everywhere, right? And actually what you are, I think, getting at is that now I have to put all of these things into GPU RAM, right? And GPU RAM is not that plentiful, right? Like let's say I have 16 gigs or 24 gigs. So the fact that and I don't just have this one cell, right? Like I have many of these cells together. So instead of like, and each one of them has, let's say, a floating point 16-bit weight over each operator, right? So I have this like massive graph, like which includes the architecture super graph that I have to put into GPU. So it's not very like memory efficient. So which again means that like if I increase the number of like operations to be more reasonable and consider more choices, this thing is not going to fit into GPU, right? So this is the thing that should bother you, right? So then this paper immediately came out like few months after that. I think less than 3 months after that. That came out like by December this was out. Where what they did is like, if you imagine that I only keep in GPU RAM one path through all the cells. So let's say I have 3 cells, right? Like, and they all have all these like operators and the weights over them. I'm going to sample a path here, like, through this cell. I'm going to sample another path through this cell and sample another path through this cell. So that gives me a full path through all these cells. And then I'm going to only at one time take that sampled path, and in practice, I will sample many of these things together, and then do the ENAS trick of sharing the weights which are common amongst all the samples so that I am efficient in forward warp and back warp, and only put those sampled paths in GPU at any given moment of time. So this basically what it allows you to do is like, so these are like the architecture parameter weights. So let's say alpha, beta, I have 4 weights. And I somehow sampled. I did a binomial distribution, flipped a coin, and said pick this one, which means everything else gets matched out, right? And I picked that architecture and trained it, right? And including all the other samples I had with me, right? So and that's why they call it proxyless, because this is the other caveat in neural architecture search world, is that all the time. What people usually do is because things are so expensive, that they find a proxy data set, which is usually like, I'm going to take reduced ImageNet or CFAR10. Nobody really does MNIST. MNIST doesn't transfer, right? Like I'm going to take something which is much tinier than the data set that I actually care about. But imagine you are in the product world, like your data sets are probably way bigger than ImageNet, right? Like let's say you have a data set which is like 10 terabytes, right? Like this is not something you would want to do even on a 10 terabyte data set, right? So what you will do is, what the common thing that people do is you subsample a very tiny data set, you train on that, find a good architecture, and then you scale up. Right, and you scale. And when I say scale up, usually what people will do is they will do cell-based architecture search, find a good cell design, and then they will like just stack many of these cells together, right? And then try that, train that on the full big data set once, right? That you can afford to do, right? And then the other things you can do is take into account explicitly, like So, and this is probably important when you are at serving time. Let's say you have a KPI. I cannot be more than 10 milliseconds during the forward prop, and you want to put that into the search, like bias the search to giving me models which are not just have good loss, but also have let's say good latency, right? Like, not too high latency, and because this is also important to me. And there are many other things. You can just put them in there, right? And that is not specific to this. You can do it. And okay. So last year, actually, in the same series, I gave this this same talk, but it was much more of a tutorial format, an hour and a half. So if you want to know more details, and including what really happens in the policy gradient updates, have a look at this. And the slides will be made available, so you will have the links.
Back to the slide that you're asking, like what the potential issues for the multiple cells put together. Is it like, for example, do they like a 0, 1, 2, 3? So they follow like a different step, right? Mm-hmm. Yeah, they follow the step. So like create like the convergence from 0 to 1, from 1 to 3 is the like difference from 2 to 3, like the errors or like how you converge the network together. Could they like have conflict on that? What's the potential issues that I want to hear more from your.
So I don't think I caught the details. Like, so are you saying that do we have like convergence issues?
No. You're asking like for this kind of architecture put the cells together. What's the potential issues? Yeah.
All I was pointing out is that if you do this thing where you maintain weights over all your architecture, your memory, the memory required for representing this graph blows up, right? Because so let's say you have a graph with n nodes and v vertices. For every vertex, you now actually have times k vertices, right? Because k is the number of operations you have in your bag, right? That you are considering, and this means this becomes like an n node times kv, like that's the size of your graph, and this is massive. Right, so you can't fit it into GPU memory.
I see. And, my question is that, like, for example, from 1 to 3 versus like 2 to 3, you reach like both from 1 and from 2 reach to the final step. What if like they have a conflict on the like the result doesn't converge, or like you have some issues with it. What if like there has conflict between these two subsets?
Which two subsets?
Like from in the graph, like from 1 to 3, 0 to 3, 2 to 3. So like you use a like it's the same. Eventually it's using the same architecture to do the work, or you use like 3 different cells. And then the result come out from different cells might have like a conflict.
Oh, you mean like? Oh, I think I understand what you mean. Like, okay, so this is a small detail, but it's an important detail, right? You can have compilation failures, right? Like, so let's say the RNN or whatever method you used, you sampled a graph, and the output. So let's say from here to here. So let's say you used like a conv 2 by 2 with stride 2. Now this downsampled it, but the tensor coming from here is twice the sample, right? So now 3 has to deal with 2 inputs coming in, which are of different resolutions, right? So this is compilation failure. Usually when I'm writing it by hand, I will just make sure that I will do the math in my head, that, oh, this will be like NC, a tensor of this size, this many channels, and I'm applying this operator, so I can do the math in my head and make sure. Otherwise, like, PyTorch or TensorFlow will throw you like a size mismatch error, right, in the first try. So what usually happens is you do all these hacks, right? Like, you make sure you will write extra boilerplate code that if these two things that are coming in are not of the same size, I'm going to do a 1x1 convolution and increase the number of filters to be, let's say, the max of these two, so that everybody gets on the same tensor size, right? So that if I add them or concatenate them or whatnot, I don't get compilation failures, right? So, but that's an important implementation delay. You can very easily get compilation failure, right? Like when you sample a network. Okay. Okay. So there's much more details here, and the slide deck I think for that is also available. Okay. So now, let's see. We have 20 minutes. So we're calling this project Petridish because, as opposed to most of the methods that I showed you, where we were doing basically something called backward search. So darts, ENAS, and that RNN, the first paper that I showed you, which are like good 3 principal components of literature, there is this implicit assumption, which in the technique, that somehow you have this super graph, that I get this like big graph, and from which I can subsample and prune down and search for a good architecture, right? And that's also human domain knowledge that you have to inject, right? Let's say you get a data set which is not vision, which is not just NLP and whatnot. So you have really no intuition on what is a good supergraph to start with and how big should I make it, right? The bigger you make it, the more search time you will take. You may be able to squeeze out more performance at the end if you're willing to spend more search budget in GPU hours, but it's also you may be very wasteful, right? So what if instead of doing backward search, which is all 99% of the papers out there, we could do forward search? And forward search basically, you should think of, we call it Petridish because like in a Petridish, we are just growing the network as needed, right? And it has the following flavor that we will start from a very seed network, let's say 1 or 2 layers. And then we will see, hey, should I add another layer or not? Right? And if I want to add a layer, what kind should it be, right? And this is the mathematical question we are going to pose, and we are going to try to find an algorithm that will do this. Now, what's the nice part about this, doing this forward instead of backward, is I don't need all that things. And second, I also can do macro search, which is the more general, like I don't need to assume that I have a cell and I have to do that. Go and reduce the search space by assuming a lot of human domain knowledge into a cell. I also don't need another knowledge of a backbone, right? Like, do I use ResNet like backbone or DenseNet like backbone? And then one nice part is, hey, let's say you had a 10 terabyte data set. You have a really good model for that. Day comes, I usually go by day, and says, hey, I have this really cool method. You should try this. But instead of trying that, what you want is like, hey, I have this method. I have this really good thing. Can you start with this and modify this instead of undoing all the work we have done to come up with a good model, right? Because we actually have put in a lot of expertise and domain knowledge to come up with this model, and right now it satisfies us, right? And so you want that property, and it's not easy to do those things with the previous methods because they have the flavor that, hey, give me a data set, I will try things and give you an architecture, right? So it's not easy to warm start from something that already exists. And then also like, explore prior knowledge. Okay, so before, how many of you know gradient boosting? Or does the word ring a bell? Okay. All right. So even if you don't know, it doesn't matter. But for this, but if you do know, then keep gradient boosting in your head, and it will come in useful, right? Like, and you can understand why. Is just like, for example, if you are training, like, for example, XGBoost or in and training like a forest of decision trees via gradient boosting, which is a very powerful method for especially for tabular data, or where you know the low-level features already pretty well, or they have semantic meaning. You are doing boosting. Boosting is this, like, general term where you are like adding weak learners one by one, right? And you are growing in scope and capacity. And this will feel, if you know gradient boosting, this will look very much like that. Okay. And in fact, one of the earliest papers. So we were inspired by this paper was 1989. I think the tech report is 1991. Is cascade correlation at CMU, and where one of the things they did. Actually, I'll skip this because I can just show you the correct method, right? And this was is you start with a small model, like, and let's say this model is tiny, and you somehow have these candidates, right? Like, and let's say these candidates are like, this grab bag of operations, right? Like a con 5x5, max pool, so on and so forth, right? And I want to know where I should add these candidates. If I were to add this, without actually adding them in, I want to know how useful these candidates are going to be if I were to add them in, right? So this is kind of like asking a very hard question. Like, well, you say you want to know how useful they are. Why don't you just add them and evaluate them, right? But that's going to run up my GPU cost, because if I add them into the network, then I have 10 different. If I have 10 different candidates, I have 10 different networks. I'm going to have to train 10 different things, and I don't want to do that. I want to like try them all at once, but without really trying them, and without affecting the original model. And then I want to see if some of them are useful, I'm going to add them in. Like, where add them in means they will just become a new network, right? A regular network with that particular thing added in. And then and now I can repeat this process, right? Of like, and I'll take that model, which has become modified, put it here, and repeat this process again. How am I going to actually do this? Because this seems like magic. So let's say I have this simple original model, right? And then this is a regular blue lines, which are regular connections. Here's really the fun part, right? Like, so let's say I have a candidate, one candidate, right? And I want to add it in such a way during that middle, the initialization phase, where I see whether it's actually what signal it can receive, it can provide, without actually affecting the gradients, the activations, or the gradients which are flowing back through the blue things. And I can actually do that. It's not that hard. Let's say this candidate, I decide to add it here. I connect it by this particular type of this dotted line, where the forward is identity, the backward is 0. So if you electrical engineering, if you heard of the term Zener diode, this is basically like that. Right? That this is a special type of layer where forward activations will flow through just as is, but backward gradients will be stopped, right? So and then we have the reverse of that, which is here, this one, which is the forward is 0, which means that if I am like doing forward prop, this is 0, this is just as it is. So the sum is just whatever the activations of B are. And then it goes through C. So we have verified that during forward activations, we don't change the activations that would have flown through the blue ones, right? Everything is unchanged. And during backward propagation, let's see. So you will get signals. This one, the backward is identity. So you will get gradients up to here, but no more gradients here, right? And the gradient from here will actually be the original one of B, right? Because there is no dependency on this candidate. So So doing forward and backward, nothing in the original graph changed, but I get to see some gradients here. And this should remind you of gradient boosting, right? Because now I can accumulate what the gradient is in that candidate with respect to B, right? Because the B is right next to it, and I can see in that candidate what gradients I'm getting. And here's the intuition, right? Like, if the okay, and this is the inspiration that comes from Scott's original paper is, hey, if this gradient is actually very highly correlated with your error, right, which gradients are, then what I'm going to do is that gives me a signal, a proxy signal, that adding this candidate is good, because then if I add this candidate into the main network and train it, it can learn weight encodings which are reverse of the error and minimize the error residue. Like, let's say right now I have some error. If I were to add this in, I have good I have it on good faith that this will be able to actually minimize the residual of the error with respect to what the target values I want, right? And you can do whatever, regression, classification, it doesn't matter. So if you decide, so that was the middle one, right? And if I decide that I want to actually add it, so I will add it in gently, because I don't want, and this is, there's no theoretical reason for doing this other than pure intuition, is that I'm going to just take out, replace these with regular connections that I should have. No more special Zener diode-like connections. But I'm going to make this one 1 and this one 0 in the beginning, the weights, so that I don't have this big disruption in the distribution of gradients that each layer sees, right? And let backprop and the optimizer figure out what the right values of these weights should be, but gently, right? From here, right? So in practice, so these are called stop gradient layers. So whatever operations you are considering, and this one that is called a stop forward layer. And then once you decide that you want them in, you are going to remove these things and create just the network, right? And with a scale value, and then let the network decide what it should be, right? And okay, so now we have yeah.
You said that you add that node gently. Do you add it in the middle of the train, or do you start training after? Do you start retraining after you add that node?
Okay, let's hold that for 3 more slides. And if you still have that problem, tell me again, right? Hopefully this will become clear. So one of the things was we wanted to, in order to be efficient, we know that we want to amortize our cost of forward prop and back prop, right? Like, this is a common running theme, right? Without that, you're not really efficient in GPU hours. So I want to try whether all these operations, so let's say I have k operations where k can be 10, 20, and I want to try whether I should have which one of these k operations I should pick here, and which one of the same k operations I should pick here. And I want, so all in parallel. So I can add them up again by doing these particular stop gradient, stop forward trick. And I'm going to just, and one of the things we do is we impose a L1 sparsity penalty on all the operations. So then we pick the operation that has the most weight amongst the k. So there's an L1 regularizer on all of this, plus an L1 regularizer on all of this, and we greedily do selection, right? So this is again like gradient boosting. We are doing greedy selection, and let's say we decided to add something together, so then it will become a part of the model, and that happens in this middle stage, right? So where we will remove them and add the the gentle introduction, and then that model will move on to the third stage where it will actually get trained fully, right? And depending upon the signal we derive from that, we will decide whether it will go back to being a parent model. So this is like a parent. These are the parents. All the candidates are being evaluated on the parents. The parents produce children, and if the children are good and seem promising, they get to be parents and see whether we are doing that. Except this will remind you of evolutionary search just because of the terms I'm using, but it's not. We are not really doing evolutionary search here, right? Which is just as much as worse as RL. Yeah, so one of the things we do is actually we do warm start, which is, so all the model weights we keep around, and just these new layers that we got added in, those layers get their new weights by backprop, they get updated, and then they're always getting incrementally trained, right? So over time, yeah.
You always add layers at the top.
No, so we can add layers anywhere, right? So that's actually part of the decision that you are saying is, that's a good question, is that you flip a coin and you say like, you pick one of the layers as the input 1, you flip the coin again, and that gives you another input 2, and then you pick where you want to be out, right? And so that means you are keeping a lot of these things together, right? Yeah, and it's important because you don't know where you should be connecting to, right? So that's part of the search space. Yeah, and this is just saying what I just said. And this whole thing is always happening asynchronously, right? In a distributed manner, that you have a pool of parents, they are going, and for every parent, we are trying to figure out which one of them which candidates we should add to which parent where, and we train them if we decide we like them, and then they get to come back. Okay, now the thing that I haven't told you is how do we decide we like a candidate, right? Like I told you the mechanism by which we would like a candidate. Right? How do we know that these candidates, when they are added, are worth going back to the parent queue, right? So here's what we do. And this is nice because this is important in the real world, is as you're trying things out asynchronously in all these queues, you are training them, you get to keep. So this is a scatter plot. So let's say you care about flops, right? This is your loss or accuracy, this is loss, and this is cost. So ideally, you want to find the Pareto frontier, right? And this could be memory, this could be latency, anything you want, or all three of them. Ideally, you want to find the Pareto frontier and know that like what is the best possible performance you can get for a given flops budget, and gives you the lowest loss, right? And look that up. And if tomorrow you get faster GPUs or your serving needs change and you are like, hey, 40 milliseconds is okay in these kind of scenarios, I want to just pick this model out, right? Like I don't want to retrain my architecture search and say, hey, give me a model which is good for 40 milliseconds, right? I already have this gallery of models which is along this approximate Pareto optimal frontier. Note, I don't know where the Pareto optimal frontier is, but as I'm training, I get to have this scatter plot. This scatter plot is building up, right? Because these are all the things that are at the end of the third queue, the child models. I train them, and I get to just plot them here, right? So the ones that I know, so if you think about it, I know for a fact that there are models, like for example, like this one. If this was a parent, it is very highly unlikely that a small modification, right, like adding a small candidate layer, would result in a model which will lower the Pareto frontier, right? Like, you know, it's highly unlikely I will go from here because I'm adding something, so which means I will go this way, but I will go have a huge drop in loss, right? Like, you know, I'm making some reasonable smoothness assumption that networks which look similar have similar performance. So which means that there is really no reason for me to add these models to the parent queue, right? Because all I really care about is here. I want to lower this as quickly as possible. But I don't know where it is, right? Exactly the frontier is. It is quite possible that this one, even though it is slightly above the Pareto frontier here, I know that it is possible. It is like, you know, this is an exploitation problem, that if I were to take this and make a dent to it, that it will go really down, right? And it will lower the frontier. And that's good news for me. And so we explicitly maintain this Pareto frontier during search, and we look for, and we take a small tolerance region around the boundary because we don't know which model may be promising. And based on the distance from the current estimate of the lower convex hull of the frontier, we explore, right? We get to add them to the parent queue and see if things will make sense. Does that answer your question? Okay. So results. Before we go to results, though, I will want before I show you numbers, it's easy to show numbers, but there's a lot of caveats in this kind of research. And right now in the community, we have this like comparison and fairness reproducibility crisis. True in just all of ML, but NAS makes it even harder. Why? Because everybody comes up with their own search space, right? So then it's hard to compare us merits of a search algorithm. Not only that, one of the things we don't address is like hyperparameter tuning, right? And it is very well known. Like let's say if you are a competitor, you have a competing algorithm, just because you have a better training subroutine, you can come up with a very good, your accuracies may be much higher, right? And if you're training subroutine for training a model, a network, has all the tips and tricks like cut out, cut mix, this kind of augmentation, has cosine warm up in learning rates and this and that makes a huge difference. You will not even be on the leaderboard if you have even though you have a great search algorithm. And so that makes a huge difference, right? What's your hardware? People are reporting GPU hours. K80 GPU hour is not the same as a V100 or like a TPU GPU hour, right? Or an FPGA GPU hour. So what's your hardware? We know we have stochasticity in training on GPUs and how many random seeds, how many trials you did. So unless you are a lab with lots of GPUs, this may be expensive for you to do and report properly. And this is also a multi-objective optimization problem, right? And that, hey, it's not just about accuracy. It's about accuracy at certain flops or memory or latency, right? We know that, hey, if you, by using very fancy distributed training, I can train a 2 gigabyte model on ImageNet and BSOTA, right? But that's not very interesting. You're not going to use that 2 gigabyte model in production, right? And that's a really uninteresting result. So there's lots of work being done. Like there's one NAS bench which came out where this is from Google and the Freiburg people whose link I was showing, where they actually went and trained close 1.8 million different architectures and put it in a lookup table. So if you want to, for example, evaluate your search algorithm, as long as you embrace that implicit search space, you can just do lookup on your laptop. You can do NAS research on a laptop by just downloading that lookup table, right? Because it's like a few MB of text. But that had things like weight sharing and darts-like search spaces cannot really work there, including our incremental thing, but more benchmarks are coming soon. And the community, I'm pretty sure, will rally around them. And it will also bring NAS research to communities who cannot afford, unless you are a big industry lab with 5,000 GPUs, you won't even touch this, right? So it'll democratize it a little bit more. Okay, results. And as I said, look at Zoff and Lee. This was 1,600 GPU days, so converted into hours. So this is, and okay, we do well on both of these fronts. This is not going to blow you out of the park, but you should not be doing vanilla RL, right? So this is not an RL problem, and we actually showed that, hey, using macro and you will see that some of these numbers have plus minus and some of these don't, because there's also variance in how people report results, right? We actually run multiple trials with different random seeds, and there's a list of best practices that one should do for reporting any results on any machine learning algorithm, right? Because we found that, hey, a lot of people are taking the best result they found during all their experiments and reporting that. That's essentially hey, I threw a number of darts, and one of them struck gold, and I'm going to report that and put up the trained model on GitHub, right? And that's not very honest, right? And you should really have variances and reproducibility. And but I would not, the results won't blow you away, because again, there's no easy way for me to show you that the gallery of models we produce, right? We are just picking one of the points that our algorithm produces and putting it on this paper, on this here, just so that I can show you some comparison, right? But this is not a very fair comparison or apples to apples by any means, right? And there's huge discussion that goes into there, right? And one of the things we were able to show that, hey, if you transfer to ImageNet, which is this process of taking a cell and adding many cells and then training it, you can actually, with macro, where you have no knowledge of backbone or cells or anything, you can do quite well as close to cell search, right? I'll skip the language modeling, and we are out of time. And just to end, there's lots of research problems, and NAS has really good useful successes, but it's no means a solved problem, right? Because if it was solved, we won't have to write architectures by hand anymore. But right now, if you are, I always tell PhD students or potential PhD students that if your research agenda in academia suddenly becomes, let me hand design a new architecture for doing object recognition, you should really rethink that, because nobody beats NAS right now on those kinds of things, right? Okay, we have we have an implementation on GitHub, but a lot of that implementation is in TensorFlow, and I know TensorFlow is not the most popular right now. So we are redoing everything in PyTorch, and we are also making the code a little bit more robust. So watch that GitHub link. We'll send out a blog post with all the right things. But one of the asks we have is you are from all over the company. Can we get access to first-party data sets, right? We don't need to publish. The method is published. We have a patent, a defensive patent on it, and interesting new data sets. They don't need to be just vision and language. They can be anything. We would love to get our hands on and work with you and try to see what we can do, right? Just for our own curiosity, right? If you have production serving needs, and we have all these kinds of you want to take into account, give me the best model which has less than 3 MB GPU RAM, right? That kind of scenarios. Would love to get our hands on that. And I will end just so that you have a bit of a break.